Can people make sure their microphones are off, please? So hi, everybody. Welcome to session 4. I'm Chair Catherine Hurley. And if you're looking to get the conference program on our website, it may not be accessible, and that's due to problems with the hosting service. It's out of our control. Session 4 is our last session today. And just quite by chance, it's got all 3 international speakers. So our final keynote of the meeting will be given by Hadley Wickham of our studio. Hadley, as you probably know, is responsible for the wonderful tools ggplot and dplyr. And you're probably also familiar with his excellent books on data science, package development, and also on using Shiny. Recently, in 2019, Hadley was a winner of the prestigious COPS Award as well. He zooms into us today from Texas. Over to you, Hadley.
Thanks, Catherine. So today I wanted to talk a little bit about dplyr, because I think one of the particularly cool things about dplyr is that it's kind of a language that has multiple possible implementations behind it. And I think this is a really interesting pattern that you see quite a lot in modeling already, that this idea that you want to separate the kind of specification of the model from how it's actually computed. You see this in the very popular and trendy machine learning toolkits like TensorFlow and Torch. You describe the machine learning model you want in some fairly high level language, and then to get the performance it needs, it's compiled into something high performance like C++ or C. It's the same kind of idea with Stan and many of the other Bayesian modeling frameworks. You describe, again, the model in some high-level framework that lets you express yourself clearly, and then behind the scenes, it is translated into something that is efficient as possible. And so that's kind of the idea of dplyr as well. And so today, I'm going to focus on mostly the 2 most important backends for dplyr, dtplyr, which translates dplyr code into the very efficient data table code, and dbplyr, which translates your dplyr code into SQL so it can run on a relational database. Now, I'm mostly going to talk about dplyr today, but these ideas are now starting to trickle in, mostly thanks to contributions from the community to functions in the tidyr package. So for example, we're beginning to provide translations for like the pivoting functions in tidyr to data table or SQL. Now, dplyr has quite a few verbs. The goal of dplyr is to help you do data manipulation. And the verbs are divided roughly into 4 categories. So we've got verbs that work with rows, that things like arrange to change the order of the rows, or various different ways of selecting the rows of interest. Then we've got columns. So you might want, if you've got a bunch of columns, you might want to select just a few, you might want to rename them, you might want to move them around. Or you might want to create new columns that are functions of existing columns. Then we've got functions that work with groups. That basically, these are mostly group by and summarize, so allowing you to group your data up into chunks of rows, and then to summarize each group into a smaller subset of rows with new summary statistics. And then most analyses, you can't work with just a single table of data, so dplyr also has verbs that work with multiple tables of data at once. So these are kind of the joins that you might be familiar with from SQL, left joins and right joins and so on. Semi-joins and anti-joins, which are about matching rows, and then the various kind of set operations of finding intersections or unions of data frames. So 19 verbs is a lot, obviously. Fortunately, you don't need to learn all of them to be pretty effective with dplyr. I think 6 are particularly important, and I'm going to quickly show those to you. So here I'm in our studio. I'm going to load dplyr and this NYC flights data set, and we'll use ggplot for a little example. So this data set is a bunch of data about flights that departed New York City in 2013. So you can see there's about 300,000 rows. And we've got variables like, when exactly did that flight leave? How much was it delayed by? Where's it going to? Who operated it? And so on. So the first thing we might want to do is filter that down. So here I'm going to find all the flights that go to the 2 airports in Houston. This is George Bush International and this is Houston Hobby Airport. So here I'm going to use the filter function. The idea of dplyr code is that you can kind of read it like a sentence. So we take the flights data set, and the pipe, I think, is best pronounced as then. So we take the flights data set, then we filter it, looking for destinations in this set of possible values. And if we run that, we see that gives about 9,000 flights that flew from New York City to Houston in 2013. So we might also want to create new variables. So this data set has the distance and the time spent in the air in minutes. I might want to compute the speed from that. So I can do that by adding a new column. So we take the flights data set, then we mutate it to add a new column called speed, which is just the distance divided by the air time in hours. So that's going to give us the speed in miles per hour. Now, if I compute this, I can't actually see the results because mutate by default adds the column to the far right of the table, and tables don't show you all of those columns to avoid overwhelming you with data. So this is a nice little example to show, nice little use case to show one of the other functions, select, which just picks out the columns that you want. So here I'm going to select distance, air time, and speed. This is a pretty pedestrian use of select. There's also a bunch of other operators where you can say, give me all of the columns that contain dip in their name. So that allows us to see, I'm not going to check the calculation here, but it allows us to see that the speed value has been calculated correctly. So that's functions that work with the rows, which in a tidy data set are the observations, functions that work with columns or variables in a tidy data set. We might also want to do various grouped summaries. So the first step in doing that is to group. And so here I'm going to group by destination. And if I just print out the result of that, nothing has really changed. So grouping by itself doesn't really do anything. Behind the scenes, it's going to generate the sort of index of the groups, but it doesn't actually really change the data in any way. What it does is affect the operation of subsequent verbs. And the most important verb you're going to use with group by is summarize. So here I'm going to say, take each group, summarize it to compute the delay, which is just going to be the average of the arrival delay. And I'm also going to compute the number of flights. So I can run that. And you can see, so for example, Albuquerque had an average delay of 4.38 minutes, and there were 254 flights. Maybe I want to find the most delayed flight or the least delayed flight, so I could change the order of the rows. And so here, this is going to arrange it in descending order by default. So you can see if you're flying to LAX, which I think is Lexington Airport, well, on average, the delay was negative 22 minutes, so it arrived 22 minutes early, which is great, but obviously there was only one flight, so not a lot of data to draw a conclusion from. So this is pretty typical. Now I might want to say, well, actually, I only want to look at the flights that have more than 365. Look at the destinations that have more than 365 flights, one flight a day on average. So I can add that into my pipeline. So take the flights data set, group it by destination, then summarize it, then filter it, then arrange it by delay. And if I run that correctly, you can see the best airport to fly to is SNA. Now, if, like me, you don't have an encyclopedic knowledge of all of the airport codes in the US, you might want to join this with another table that has the names of those airports. And so this data package also includes a data frame with information about the airports. And so I'm going to want to join that together so I can see the name of the airport, not just its FAA code. So I'm going to start just by taking that summary I computed before and saving it to a variable, so I have to keep recomputing it. That's just the same data I showed you earlier. And now I want to join it. I want to combine those two data frames. Take the destination delay, do a left join. A left join is kind of the default join because it keeps all of the rows on the left-hand side. And we're going to join it by, in this case, the variable names are different. So we're going to join the destination variable from the delay data set to the FAA variable. And then I'm just going to focus on some of the variables that are most interesting. So if I do that, you can now see SNA is the John Wayne Airport in Orange County, California. You can also see we've got this airport STT, which has a missing value for a name. And this is because we've done a left join. We've said we want to keep all of the rows on the left-hand side, all of the rows in this data set. So that means we're going to have to fill in some missing values when there isn't a match. And that kind of brings you to your next question, where you're likely, well, you might wonder, well, if this airport doesn't match, what other airports don't match? And so this is a really great use for an anti-join. So anti-join, much less commonly known join, but it basically gives you all of the rows that don't have a match. So I'm going to start by using another one of these functions, which I haven't talked about, distinct, which is just going to give me all of the distinct values of the destination variable. And then I'm going to anti-join it to the airports data set. So that's going to tell me all of the destinations in the flights data set where I don't have a matching row in the airports data set. And so there's 4 of them. You know, if this is a real analysis, I'd then go away and add those rows to the airport data set so I don't have anything that's missing. So that's kind of a whirlwind tour. I guess I showed you anti-join instead of semi-join, but semi-join basically gives you all the rows that do match. Anti-join gives you all the rows that don't match. This pair of functions, really, really useful when you're trying to figure out what does and doesn't match between pairs of tables. Now, dplyr is great when you're working with kind of moderately sized data sets in R. What happens when the data gets big? And you know, I don't think there's a great threshold, like there's no sort of magic number for what makes data big. I think there are kind of 2 signs that you're dealing with big data. The first is you spend more time computing the data than thinking about what to compute. You think in most smaller analyses, most of your time you're trying to figure out what you should do next, or what do the current results mean. With big data now, you're going to think about what to do, tell the computer to do it, and it's going to sit there and chug away for a few seconds, or a few minutes, or a few hours. The other sign of a big data problem is that just moving it around is a hassle. Like if you've got gigabytes or terabytes or petabytes of data, that's just a pain to get that data onto your computer so you can work with it. And what that often means is instead of moving the data to you, you want to send the computation to the data, and then just bring back the smallest summary or subsample or selection back to your computer to work on it there. And dplyr kind of helps with that because it tries to provide this smooth transition through various different backends. So what I've showed you so far is just the built-in implementation and works with data frames. Next, I'm going to show you dtplyr, which works with data table, really fantastic, very, very efficient R package for working with larger data sets. Data table still requires that all of the data fits in memory. So if you've got larger data sets, it might live in a database. You can use dbplyr to write SQL code for you. And then I'll briefly show you multidplyr, which allows you to spread computation across multiple cores. And then I'm not going to talk about, but another useful package if you've got really large data sets, is sparklyr. Sparklyr works with a Spark tool, which basically spreads your data over a cluster of computers and uses the individual computer on each computer as effectively as possible.
Esos son 200 euros.
So let's look at dtplyr. So you may or may not have heard of data table before. If not, it's a really, really fantastic R package designed around basically making data frames as fast as humanly possible. Data table also kind of chose to optimize for typing speed, so it has a very, very concise syntax. So I showed you, very briefly earlier, those kind of 19 key dplyr verbs. Data table really has one key function, which is the single square bracket. So the goal of dtplyr is to kind of say, like, if you already know dplyr syntax, can we get you the benefits of data table performance without having to learn much about it? So the idea really is you write dplyr code, or you keep writing the same dplyr code you've been using already, and then dtplyr is going to translate that to data table code for you. So let's take a look at what that means. just going to restart my R session, load dplyr. This time I'm going to load dtplyr as well, and that same data set. And the first thing I have to do is take my existing data frame and turn it into a lazy data table. We'll come back to what that means in a little bit more detail shortly, but basically it's going to try and put off as much work as possible to the last possible minute. Not a great attribute in people, but laziness in general is a really good strategy. So I can still do all of the same things I did before, but now when I run that code, you'll see there's an additional line which tells you, which shows you the data table code that it generates. So subsetting by rows in data table looks very similar to subsetting by rows in data frames, except you don't need to put the data frame $ in front of the variable name, and you only use, you don't have to put a comma. You can mutate to add new variables. This uses data table's kind of special walrus operator syntax. This is kind of a weird vestigial feature of R. We call it the walrus operator, because it kind of looks like a walrus on its side. Various more complicated things, group summary just translates that to the standard data table syntax using key by or by and a summary. And of course, we can string more things together. We could say, give me all the flights, and then arrange in descending order of delay. And that would just keep on generating more and more complex data table operations. And it does all of this for you. By and large, you don't need to care that it's data table in the background. But I wanted to come back briefly to this idea of laziness, because it's a pretty important feature of the package. Basically, when you run code like this, no computation is actually going to happen. dtplyr is only going to evaluate the data table code at the last possible minute. So the times it does this is if you print it, just because when you print a data frame, you really want to see what it is so you can iterate. Or you can say, well, don't evaluate it, just tell me what's going to be computed with the show query function. Or you can force computation by converting it to a regular Tibble data frame or data table. But the advantage of this laziness is that it gives us the ability to do optimizations across multiple steps in a pipeline. And a really good example of this is when you want to both filter the rows and the columns at the same time. So when you do this with regular data table code, what it's going to do is first filter the rows, and then it's going to filter the columns. And that's a little bit inefficient because it has to filter all of the columns that you immediately drop in the next statement. But data table has a special syntax for this because you can subset by rows and columns simultaneously. And so this is one of the ways that allows data table to be more efficient, because it can do more in one statement. And that means there are more opportunities to take shortcuts, basically. And so dtplyr does its best to take advantage of that. Because of this laziness, it's going to string together all of the secret operations in the pipe, and it's going to try and find the fastest way to combine them. How can it make the smallest number of data table expressions that's going to give you the most performance? Now that kind of brings up an important question, which is like, there's obviously some cost of translating your dplyr code to data table code. What is that? And I think the most important thing here is that the translation cost scales with the length of the pipeline, but the computation cost scales with the size of the data. And that means, and by and large, like this translation cost is very small. And as your data gets bigger and bigger and bigger, that cost is fixed. So as a proportion of the total time, it gets smaller and smaller and smaller. So it turns out this is surprisingly efficient. Now there's a kind of another cost, which is maybe dtplyr doesn't generate the most efficient translation. I don't really know how to measure that, but generally, like when we discover that, it's generally straightforward to fix, and then the next version of the package gets that better performance. There's also some cost associated with making copies. Data table has this kind of reference semantics. So most of the time you're modifying the same in-memory data set that reduces the amount of memory usage, which can be convenient when you've got very large data sets. That's kind of different to the dplyr philosophy. So dplyr has to make a few extra copies. You can opt out of that if you really need to. But in short, dtplyr is surprisingly efficient. So that's dtplyr. That allows you to work with like larger in-memory data sets using all the great performance of data table. What happens when your data gets bigger than really big, so it can't even fit in memory at once? Then it's likely that your data is going to be stored in a relational database, and you can turn to dbplyr, whose job is basically to write SQL for you. So generally, if you're going to connect to a database in R, your code's going to look something like this. You're going to load the dbi package. Dbi package, same kind of idea as dplyr. dbi provides this sort of generic interface that works with every database. It provides the key verbs that you're going to use on databases. And then when you connect to a database, like here, I'm connecting to SQLite, you will use a database-specific package that provides the implementation. So this means regardless of what database you're connecting to in R, the code is going to look very, very similar. Now here I'm just using SQLite because it's really, really simple, and I can create this sort of transient in-memory data set and copy the flights data in. This is really great for examples. Obviously, in real life, you'd be connecting to a MySQL database or Oracle database or SQL Server or Postgres data that someone else has set up and run for you. But once you've connected that database using dbconnect, most of what you're going to do is write SQL code. So here I'm selecting 3 variables from the flights data set where the rows have this value. And you can learn SQL pretty quickly if you're already familiar with dplyr, because there are a lot of similarities. And that that's not a surprise, because dplyr was very much inspired by the SQL language. So pretty much any SQL is a huge language. There's lots of stuff you can do with SQL that basically you as a data scientist is never going to care about. 99% of what you'll do as a data scientist is write select queries which pull data out of the database. And the goal, the idea of dbplyr is to take your dplyr code and automatically translate that to SQL for you. And you might wonder why bother? SQL's so easy to learn, then why not just learn it and write it yourself? Well, that's fine, but there are a bunch of little really frustrating differences between R and SQL that when you're having to switch between them just cause you no end of hassle. Like for example, in R, if you're comparing equality, use 2 equal signs. In SQL, use 1 equal sign. In R, you can use single quotes or double quotes for strings. In most SQL dialects, you have to use single quotes. In SQL, mean is called average. Instead of using the caret, use power. Instead of the way that you represent integers is different. There's just a bunch of little differences that are really annoying. Not because R and SQL are so different, but because R and SQL are so similar, and you get this kind of constant confusion in your head. The other thing that's really annoying with SQL is when you look at a SQL query, it gives you absolutely no insight into how that query will actually be performed. So when you look at a query like this, where I'm just computing the average delay by destination, and then finding all the destinations that have a average. So only for destinations where the departure delay is greater than 10 minutes. If you look at how this is actually computed, the order is completely different, because you have to start by specifying the data set, then you do the where statement, then you group by, and then you do the select. And this makes it kind of hard to build up a good mental model of what's actually going on when you write a SQL query. Whereas if you write this with dplyr, it's very, very obvious what's going on. And in this in particular, this kind of query, does this happen before or after the summaries? Obviously, for this to work, it has to happen before the summaries. But when you write it as after the summaries, if you want to actually do that filtering in SQL after the summaries, then you have to use the having clause instead of the where clause. So there's just all of these little minor nuisances that SQL exposes you to. So let's just take a quick look at that in practice. So again, I'm going to restart my R session. This time loading dbplyr, and I'm going to create a database. If you've never worked with databases before, they can seem quite intimidating. But getting up and running with a SQLite database, as you can see here, is like literally 3 lines of code. Really, really simple. And now I'm going to create objects that map to my database table. So if I print these out, again, they look exactly like tables, but you'll see this is actually backed by a SQLite database. So again, we can run some dplyr code. I'm going to use this show query function again, same function I use with dtplyr. It's going to take this dplyr code and tell me what it's translated to. So group by destination, summarize, tell me what you did, converted to a select query with counts and averages from the flights dataset grouped by guest. One of the cool things about this is it works with the new across function in dplyr 1.0. So for example, if you wanted to summarize to compute the mean of every column, that's going to generate this rather verbose SQL query that would be a pain to do by hand. SQL has no built-in capability to say, give me the average of every variable. And so this is really quite convenient. Now, in this case, this is totally meaningless and wouldn't work because you can't compute the average of like the carrier, but in real cases, you'd filter this down a little bit more specifically. The translation is smart enough to automatically add subqueries where needed. If you use dplyr a lot, you're kind of used to this facility where when you create a function with create a new variable with mutate, you can immediately use it. That's not the case in SQL by default. When you create a new variable, you can't use it. And so you actually have to wrap the whole thing in a subquery. So you've got to put a query inside your query. Obviously this is going to be like painful to do if you're writing it by hand. dbplyr just takes care of it for you. And then finally, just one little example kind of showing you all the major clauses of a select query. I'm going to filter, I'm going to select, I'm going to arrange, and I'm going to just look at the first 6 rows. That generates a select clause, a from clause, a where clause, an order by clause, and a limit clause. Now, as well as translating these kind of high-level verbs, you also have to be able to translate lower-level functions. So there's also a bunch of logic in dbplyr to translate the expressions that you write in R to their SQL equivalents, which can also vary quite a bit from database to database. So dbplyr has a bunch of knowledge about how different SQL dialects differ. So when one function that differs a lot between databases is the paste function for joining strings together. So the default kind of ANSI SQL, the SQL standard uses concat WS, but if you're using SQLite, it translates it to these double bars. If you're using SQL Server, it uses plus. If you're using Microsoft Access, it uses AND. And so dbplyr just takes care of all of this like minor variation for you with a bunch of translations baked in. So Microsoft Access, SAP HANA, Hive, Impala, SQL Server, Oracle, Postgres, Redshift, Teradata, Snowflake. And it's pretty easy to add new backends if there's a database that is not covered by this. Like most of the time, it's pretty easy. It's just a little tedious because you've got to do a bunch of research to figure out what's the closest equivalent for these R functions to these SQL functions. Okay, so that is dtplyr, which translates to data table, and dbplyr, which translates to SQL. One very, very quick last demonstration. I'm not even going to demo this. I'm just going to talk about this as this multidplyr function, which allows you to create very lightweight clusters on your current computer. So here I'm going to create a cluster of 4 R processors. So that means I can use 4 cores on my computer. And multidplyr introduces a new verb called partition, which is going to spread your data across those different processes. And so that means when you work on them in parallel, you're going to get higher performance. So I'll just quickly show that. I've made up this function, you know, obviously in real life, you'd have something a little more interesting than that. But if I run this locally, you're going to expect it to take about 2.1 seconds because I've got 100 destinations and I'm computing this mean for every group. And if I do that, indeed, you see it takes about 2.1 seconds. So I've got this slow function. I don't want to run it all on one core. I want to spread it across as many cores as possible. So I create a cluster. I partition my data across that cluster, set up all of the, I've got to copy that function to the cluster. I've got to load dplyr in those functions. And then I can run that summary again. And you can see it now takes about 8.62. So 2.2 divided by 4. So we didn't get a 4-fold speed up. This is pretty common when you're working with, when you're trying to parallelize across multiple cores, just because there's some cost of communication and it takes a while for things to spin out. But generally, like the longer the tasks, the more benefit you're going to get from speeding it up across spreading the work across multiple cores, and multidplyr just makes that really, really easy. The other thing which you kind of have to do once you're done with that is you have to retrieve all of the data back from the individual cores back to your computer using a function like collect. Again, that's going to add a little bit of overhead. I think one of the most important things about working with big data is recognizing that moving data around is expensive. And so you want to do everything you possibly can to minimize that. So for example, when I run this code, when I run the summary, again, multidplyr is just going to leave that code in those individual workers. It's not going to bring it back. So that if I do something else, if I do a filter statement, delay is less than 5, so it's going to spread that work across the individual cores as well, and then only bring back a smaller amount of data. And that did actually work here, which is reassuring. Okay, so that was kind of a whirlwind tour. I've talked a little bit about big data problems. So I think, you know, you have a big data problem if you're spending more time computing on your data than thinking about what to do, or just of moving that data around as a hassle. And you're starting to think, well, instead of moving the data to me, can I send the computation that I want done to the place where the data lives? And we're seeing kind of more and more examples of this in the sort of the big data field generally. You know, it's pretty common now to store large data sets in Amazon's S3 system. Now Amazon also provides the system called Athena, which lets you query that data. So rather than having to bring every data set back to your individual computer so you can find just the handful of rows you need, you can use Athena to do all of the computation on Amazon servers and then just bring those specific rows that you really care about back to your computer. dplyr is kind of designed to help you manage this transition by allowing you to write the same code or very similar code, regardless of how big your data is and where it lives. You use dtplyr to generate data table code, dbplyr to generate SQL. Multidplyr, slightly different, but same idea, allows you to spread computation across multiple cores of your computer, and sparklyr for spreading computation across multiple machines. The thing that I think is kind of fascinating, and the thing that I have to say surprised me about all of these backends, is that they actually work. It wasn't clear to me when I started this project it was actually possible to kind of take, you know, a decent subset of dplyr expressions and translate them, for example, to SQL, because there are many, many, many functions in R that have no SQL equivalent. But you know, because there is this like very easy transition, you can write as much of your code in SQL as possible, so you get the smallest subset of rows or subsample of rows that you need. And then you can just you know, painlessly, seamlessly switch to writing R code for all of the stuff that you can't do in SQL. So I think this like hybrid strategy really, really pays off. You can write very similar code. You need to think a little bit about how the data is moving around. But I think on the whole, dplyr has been really successful at giving you this common language for manipulating data that is fairly well separated for how that computation actually occurs. Thank you.